Hi, Dr. V and everyone. Today we will present about closed-loop control of circulating drug in live animal. First, let me introduce my group members. Tasnim, Shafiqah Nasuha, Nur Azza Shazbani, Huzaimah, and Nur Almira.
Abstract for this project is current methods of drug dosing rely on physical parameters such as sex, age, and weight that do not account for genetic and physiological difference among individual patients. This difference can greatly affect how drugs are processed in the body and can result in ineffective underdosing or toxic overdosing. Here we describe a generalizable closed-loop system consisting of a biosensor, controller, and infusion pump, and a model of drug pharmacokinetics that continuously monitors and adjusts the concentration of a given drug in the body. Okay, for introduction, closed-loop control of circulating drug levels in live animals is to adjust drug levels in live animals to automatically using real-time sensor. As a programmable infusion pump injects drug into the animal, the bloodstream is sampled continuously by our real-time biosensor. Current protocols for predicting the optimal drug dose for a patient generally rely on easily obtained physical parameters such as sex, age, body weight, or body surface area. Unfortunately, these parameters do not account for individual difference in pharmacokinetics. That is how the drug is processed by the body, and pharmacodynamics, how the body is affected by the drug, which can lead to ineffective underdosing or toxic the body is affected by the drug. It is an especially important problem for drugs that exhibit therapeutic windows within which the concentration of drug in the bloodstream is both effective and safe, such as chemotherapeutic, immunosuppressants, anticoagulants, insulin, and aesthetics. The resulting electrochemical measurements of drug concentration are listed by our feedback controller, which calculates the infusion rate needed to maintain the desired circulating drug set point at any time, automatically adjust the infusion rate accordingly. Okay, next.
Next, I will continue on state of art. Okay, the first controller used is feedback controller. Its resulting electrochemical measurements of drug concentration are analyzed by our feedback controller, which calculates the infusion rate needed to maintain the desired circulating drug set point at any given time and automatically adjust the infusion rate accordingly. Next, we use pi controller to ensuring patient safety will also be a critical step in clinical translation. Although the simple pi control algorithm used in this work was sufficient to demonstrate proof of concept performance, safe clinical use would require more thorough characterization of non-linearities in the control system, such as pump output saturation, which could result in pi controller wind up. This wind up could result in overdosing, but it should be noted that there are well-established anti-wind up measures that could be readily implemented in our pi controller. As an additional countermeasure for patient safety, it should be possible to prevent accidental overdosing by configuring hardwired limits into the infusion pump that triggers shut-off of drug delivery in the event of controller error. The transfer function of the plant we use is feedback loop can be modeled in silico. Next. Okay, this model comprises the controller with professional integral and derivative in Kp, Ki, and Kd. The infusion pump drug PK with an effective dilution volume Vd and exponential alpha and beta phase and measure rate. And the real-time biosensor S denotes the complex Laplace variable in transfer function form. Simulation based on this model enabled in silico controller simulation and tuning for control in vivo. We use our mathematical model of our closed-loop system to simulate drug plasma clearance in rat and thereby identify appropriate KP and KI controllers setting that enable responsive and stable concentration control. The optimization method used are study design, sensor fabrication, thermal probe preparation and immobilization, fluidic instrumentation, voltmetry, signal processing, sensor activation, and characterization, real-time analysis and control problem, control algorithm, design and implementation. Okay, one advantage is the fact that the use of feedback makes the system response relatively insensitive to external disturbance and internal variation in system parameters such as temperature. It is thus possible to use relatively inaccurate and inexpensive components to obtain the accurate control of a given process of time. However, system stability can be a major problem, especially in badly designed closed-loop systems, as they may try to overcorrect an error which could cause the system to lose control and oscillate. Next presenter.
For methodology, I will explain about the mathematical modeling. The mathematical modeling is consisting of the controller with proportional which are integral and derivative gains, Kp, Ki and Kd, the infusion pumps, the drug PK with an effective dilution volume which contains exponential alpha and beta phase elimination rates. It also has the real-time biosensor where it denotes the complex Laplace variable in transfer function form. Next, I will explain about the block diagram. The closed-loop infusion control system consists of three elements in order to achieve closed-loop feedback control. First of all, the use of controller is to control the drug concentration, where it uses a proportional integral derivative, PID, to determine the rate of drug that needs to achieve the concentration that is needed by the live animal. Next, the infusion pump that is used to deliver the drug into the animal with the desired concentration by the controller. Besides, the real-time biosensor, where the device allows continuous measurement of drugs directly from the bloodstream. The system was designed to have a rapid response time, where it is capable in reaching and maintaining changes of the concentration drug, which is doxorubicin drops that occurs within 10 minutes. Other than that, it also was configured to maintain the stability of dox concentration for more than 2 hours continuously. It is also designed to achieve robust control over a wide range of pharmacokinetics PK. In order to achieve it, a careful design and optimization are required in both of stability and robustness of biosensor and the controller. So, in this project, the biosensor uses electrochemically tagged upthermos probes that are designed to undergo the reversible conformation change on binding their drug target. Closed-loop control system requires real-time processing of sensor data where we make enhancement to the biosensor construction. Firstly, to eliminate any lagging in measurement processing where the program can convert the data from the biosensor to dox concentration measurements. Secondly, the microcapillary tubing is used to minimize the fluidic transport lag between the animal's blood and biosensor, as well as a differential measurement algorithm is implemented to ensure the measurement accuracy. Next, the interior surfaces of the microfluidic flow channel is modified with a heparin-based anticoagulant coating to ensure the stability and uninterrupted collection in vivo measurement for several hours. So, we design our system control algorithm around a classic PID controller which calculates the necessary rates of the drug infusion by comparing the measured in vivo concentration to the desired set point. The PID controller calculates pump output, which consists three terms, which are a proportional term, an integral term, and a derivative term. By tuning the gain setting properly, the controller can balance the response time and stability even when the drug's PK varies unpredictably. In order to tune the controller gain settings is evaluated differently using a simulated model of the closed-loop system. It describes the behavior of each component in the feedback loop, including the biosensor, controller, and infusion pump. By using the population average dox PK parameters for rabbits, we tune the controller Kp and Ki gain setting to achieve the shortest response time without having any interruption, such as overshoot and steady-state oscillation. We then simulated the controller's performance and showed that it can achieve stable presence.
Okay, this is the result and the discussion of our project. From this figure, it shows the time domain graph for the closed-loop infusion during acute drug-in-drug interaction. A and B show us the graph for traditional infusion that we are in market nowadays. It showed that the drug infusion level was always too high and too low from the pre-described for the animals. This is not good for the animal because it can be harmful to the animal health. Therefore, by using the upgraded closed-loop infusion system, the drug infusion level can be controlled as follow the prescribed drug level. It also not just follow the drug level, but it also follow the time that have been set so that there will be no overdose issue and the animal will not feel any pain. Thus, the farm output data for the measurement are shown in E. So this project is a demonstration of a technology that achieves a precise, personalized drug dosing through controlled system. As a proof, the circulating result level of the chemotherapeutic agent drugs are directly controlled in live animal, and the capability to reach and maintain the broad range of concentration set point in the bloodstream as function of the time. This system can automatically adapt in the real time to individually physiology difference, compensating for PK variable and even drug in the drug interaction. This is because the real-time biosensor use the probe that can read and be exchanged the measure of drug. The result with dogs suggests that this system would be well suited for controlling intravenous drugs that are efficiency and toxicity are closely tied to circulating level in the blood. Result, the rapid measurement time of this system could eventually make it useful for dosing drugs with rapid PK of pharmacodynamic, especially in situations where the patient physiology can change rapidly and unpredicted. Below, Figure 5.2 is the initial proof of concept that the successful of controlled drugs concentration into mammalian species, that is rabbit and rat, with dramatically different physiology and PK characteristics. Ensuring patient safety will also be a critical step in this clinical term. Even though the sample PI control algorithm we are used in this system, it was sufficient to demonstrate such clinical use would require more thorough characterization of nonlinearity in the control system such as pump output saturation, which could result the PI controller wind up. This wind up could guide us to the overdosing, but it should be noted that there are well-established anti-wind up measures that could be readily implemented in this PID controller. There are some limitations at the performance where the PI controller is sensitive to time lag through the feedback loop. The use of ex vivo biosensor chip result in small but unavoidable time delay arising from fluidic transport lag as the blood flow from the animal bloodstream to the chip.
So, the conclusion from our discussion, taking everything into consideration, we envision a number of potential improvements that could further expand the clinical utility of our system. First, the current system is designed to control infusion based on only measurements of free drugs, molecules in the blood, but levels of metabolites and plasma protein-bound drugs molecules can also be important indicators of pharmacological for activities pharmacological certain drugs, including dogs. Thus, it will be useful to integrate multiple aptamer probes that make it possible to control infusion based on combined measurements of free drugs as well as metabolites or drug protein complexes. These would require development of metabolite-specific aptamers, which could be readily multiplexed onto our biosensor using established methods, as well as multi-input control algorithms. Second, we designed our system to regulate infusion based on measured levels of drug in the intravascular compartment, which is appropriate for the drugs whose efficacy and toxicity are clearly correlated with plasma concentration. To control drugs with more complex tissue contribution and metabolism pathways, future versions of our system could utilize PK models that predict drugs concentration in the target organ, a strategy that is being employed in artificial pancreas systems. Finally, in the present configuration, our system in an ex vivo system that will be well suited for use in clinical settings. However, future iterations of the system could incorporate implantable sensors and infusion device to enable continuous, minimally invasive dose regulation as a patient goes about their daily activities. With such advance, we believe this technology could fortunately transform the treatment of chronic condition. That's all from me and my group mates. Thank you.